Okay, so like I was explaining, if you want exactly one of the two, then it's going to be the probability of the first person being a high risk and the second person being a not at risk, okay, or the probability that's plus the probability of what the first person being a not at risk and the second person being a what? A high risk, okay? Now, we know that if there are two persons, okay, selected, there are two different human beings, okay? So the fact that one has this person is high risk, okay, does not mean that this person is also going to be what? High risk, okay? So we are saying that there are two independent events. This and this are two independent. So if the first person is high risk, okay, he's independent of the second person being not at risk. So we are dealing with independent events here. If independent, then we can also conclude that the probability is just a product of the individual event, the product of the probability of the individual event, okay? So this will give us what? P of H times P of N plus P of N times P of H, okay? P of H we know to be 0.1, so we'll put that here. P of N is 0.9, we'll put that here, okay? And then it goes 0.9 times 0.1. This should give us what? 0.09, okay, plus 0.09, okay, which will be equal to what? 0.18. So this is the chance, okay, of selecting an individual, okay, who has a high risk, okay, from exactly two people, okay, and that is the chance, okay. So there's an 18% chance, okay, that one out of the two people will be at risk of a heart attack, okay. Okay. Now we'll look at the Bayes theory too briefly, okay. From what we have studied so far, then it simply means that the probability of A intersection B is also the probability of B intersection what? A, okay. So if that is the case, then we can also say that then the probability of A giving B times B, which is for this, okay, times B is also equal to what? The probability of what? Is going to be the probability of what? B given A times the probability of A, okay? By simplification, we can also write, just dividing through by P of B, we can write that P of A given P is equals to P of B given A times P of A over what? P of B. Okay, that is for the Bayes rule. Okay, there is another sample here. Okay, we have, he says, an electrical system of 4 components, okay, illustrated in the figure. Okay, the system will work if the components A, B, and either C or D, okay, works. The reliability, that's the probability of working of each component, is shown in the figure. Find the probability that the entire system works, okay? Yeah, clearly we've been told that the system will work if A, okay, and B, and what? And either what? C or D is what is working. Okay, good. So that is a probability we need to find, the probability of this component, okay, of this relation. All right, okay. So in doing so, we can simply write, okay, P of A and B and C or D working, okay, is just going to be P of A times P of B times, you see, the components are independent of each other, okay? And there are three independent components. So we can, that helps us to write P of A times P of B times P of C or D, okay? P of C or D, right? But we also know from P of C or D, okay, that P of C or D, okay, is equal to what? 1 minus what? P of what? C or D what? Complement, okay? Are you getting it? Right. So, which also means that we can replace this with that, okay? But from De Morgan's rules too, we know that this should be 1 minus P of C or D, okay? It's simply what? P of C complement, okay? Intersection what? The probability of, or if you like, okay, you can re-express this. That will be C complement intersection D complement, okay? So when you expand, you get probability of C complement. Let me rewrite this. Okay, intersection what? D complement, okay? Yeah, and then since the events are independent, we can write what? P of what? C complement, okay, times the probability of what? D complement, okay, good. So that will be 1 minus this, right? So we replace the whole of P of C or D with this whole term, which gives us this, okay, good. Now we know that the probability of C was, or even C, yeah, the probability of C, reliability of C was 0.8, okay? The reliability of C was 0.8. So it means that the reliability of C complement will be what? 1 minus 0.8, okay, which will be 0.2, okay? And then the probability of D complement will also be 1 minus 0.8, which is 0.2, okay? Now, if we should multiply this and this, okay, that will give us 0.81 times 0. This will 0. You have to do that calculation for me. This will give us 0.04. Okay, 1 minus that should give us 0.96. Okay, times 0.81 will give us 0.776. Okay, good. So that is the probability that the entire component will work. I hope you have your calculators to be checking that, okay? So try and check it briefly before we proceed. Try and check if you had the answer before we continue. Okay. Yeah, I'm sure you finished checking by now. Yeah, let's continue. Okay. So the next concept we're looking at is the concept of a random variable. Okay. Now, a random variable is a measurable function, okay, from a sample space of events to a measurable space of values, of possible values of the variables. Okay, in summary, we say that this is a function. It is a function which maps the sample space to real number values. And when we say a random variable, we are talking about a stochastic variable, okay? And a stochastic process, okay? And stochastic just means a process with chance, the chance of occurring. So a random variable is a variable with a chance of what? Occurrence, okay? But this time around, it is a function because it's a rule, it's a function which will map the elements in the sample space to real number values. Okay, let's see what this really means with a demonstration. Examples of random variables are as follows: the number of packets that arrives to a destination, the waiting time of a customer in a queue, the number of cars that enters a parking each hour, just a minute. Why is this thing behaving like that? So, okay. So number of cars that enter a parking space each hour. Okay, all of these are random processes or random variables. Now let's take an example. So we are saying that if we should toss two coins, okay, and we define the random variable or the random function as observing the head, okay, if we define our RV as observing the head, okay, then you see, per our definition, we said it assigns to each element in the sample space a real number value, okay? So first we need to identify our sample space. We need to write it out. So if we have two coins tossed, then the sample space of such an experiment is going to be head, 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 head. Okay, we have head, tail. We have tail, head. And we also have tail, tail. Good. So the question is, how do we do the assignment? The rule says that we are observing a head, okay? So we are only going to count the number of heads in each outcome. So we come here, how many heads do we have here? We have 2 heads, okay? There are 2 heads in this outcome. When you come here, how many heads do we have? We have just 1. When you come here, there are how many heads? You have 1. And then when you come to the last outcome, there are what? 0 heads, no head at all. So what we are saying is the possible values of this rule, this function will be what? 0, 1, and 2. 0 simply means there will be no heads, or there can be 1 head. That is 1 means 1 head. And then 2 means there can be 2 heads. Okay, good. So we write the random function as what? 0, 1, and 2. 0, where x belongs to the outcome 2 tails. That's tail, tail. And then 1 if x belongs to the outcome a head and a tail, or a tail and a head. And then 2 in the case where x belongs to the outcome 2 heads, so a head and a head. Okay, so that becomes the random variable of the process, okay, or the random function of the process. Very well. Let's take another example. So we ask, so what if we have 3 coins? It's the same principle. If there are 3 coins, then our sample space will be what? Head, 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 tail, head, tail, head, head, tail, head, 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 tail, 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 head, tail, 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 head, and tail, tail, tail. Okay. So if you having difficulties in doing this, you can use the tree diagram. Okay. So for the first occurrence, we can have head and tail. That's for the first coin. Second coin. Okay. So first coin. Second, third coin. For the first, you have 2 possible outcomes. On the second 2, you have 2 possible outcomes. Okay, sorry, and a tail. Okay, so head and a tail. And then on the third as well, we have 2 possible outcomes. So we have head, tail. We have head, tail. We can have head, tail, head, tail. And then finally we have head, head, and what? And a tail. Okay, so this will give us the combinations. So the first one will be head, head, head. Okay, then the next one will be head, head, tail. Okay, good. Then you take head, tail, head, head, tail, 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 head, head, tail, head, tail, head, tail, 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 head, and then tail, tail, tail. Okay, good. So these are the this a way of generating what? The combinations or all possible outcomes of the experiment. Okay, good. So because our rule is observing a head once again, okay, we'll count the number of heads. There are 3 heads here. There are 2 heads, 2 heads, 2 heads, 1 head, 1 head, 1 head, and then what? 0 heads over here. Okay, good. So it means that there are 3 unique outcomes. Either we have 0, 1, 2, or 3. So that makes it 4. Okay, good. So we say that the random variable can have the possible value 0, 1, 2, 3. It is 0 if x belongs to the outcome tail, tail, tail. It is 1 if x belongs to the outcome Okay, head, tail, 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 head, tail, 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 head. Okay, and then it is 2 if X belongs to the outcome, head, head, tail, head, tail, head, and then what? Tail, head, head. And then it is 3 if X belongs to the outcome, head, head, and a head. Okay, that is how you generate the random variable of the process. Okay, any question on this point before we continue? Any question before we continue?
No, sir.
Very well. So in that case, the next thing we'll be looking at is the concept of probability distribution. But before we do that, we need to understand that there are 2 main types of processes. Okay, the first random stochastic process. We have discrete random variables, and then we have continuous random variables. Okay, now a discrete random variable is a random variable which takes on finite or countably infinite number of values. So the outcomes are what? Finite, okay? Or let me say they are countable, okay? So for example, the number of cars that enter into a park, we can count them within an hour. We can count how many cars have entered into the park, okay? That is what we mean by a discrete random variable, okay? Good. Then we also have continuous processes, okay? Continuous processes, which basically, so for example, something like the lifespan or radioactive decay or temperature, okay? Things which happen at a rate that we call as what? Continuous random variables. So modeling the time to the first call, okay? The time to a first call at a local police station is what? A continuous random variable, because it's a function of time, okay? Good. Now, probability distribution of a random variable, okay, is a sequence, okay, of the xi are the possible values of the random variable together with the assigned probabilities to each xi, okay, to each point xi, or better still, to each outcome. Okay, so a list of the outcomes of the random process with their corresponding probabilities is referred to as what? The probability distribution of the process. So in a tabular form, we can write this. Okay, so S1, which is probability, S2, which is probability, dot, 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 to Xn, which is what? Probability. Okay, good. Then you take note of the notation too. You can see probability this time is written in small letters. Okay, very good. Now in the next slide, I'm going to explain that to you. Okay, so what are we saying? We are saying that the probability distribution of a discrete random variable has a special name, which is the probability mass function. Okay, so if the random variable is a discrete random variable, then we call its probability distribution as what? The probability mass function. Okay, good. And then what you should also note is the probability of the outcome xi can also be written as what? The probability, capital P, of the random variable assuming the value xi. Okay, so you take note of the notation. So P of the random process, assuming xi, the value xi is equals to the probability of xi, of the outcome xi. Okay, then we have said earlier that as a property of the probability distribution, the probability of any event lies between 0 and 1. And also the sum of all probabilities is equal to what? Is equal to 1. Okay, very well. And then the cumulative distribution function, which is the CDF, okay, written as the probability of the random process, okay, being less than or equal to a particular value. Less than or equal to means all previous values to the point. Is equals to the summation of the probabilities before we get to that particular point X, okay? You sum all the probabilities before we get to the point X. Good. Now let's take a very simple example to construct the first probability distribution, okay, and then continue from there. So we are told that a fair coin is tossed 3 times. If X is the number of heads that show up, find the probability distribution of what? Of X, okay? A fair coin is tossed 3 times. So we are conducting, okay, tossing 3 coins, and we expect 3 outcomes at a time, okay? So it says if X represents the number of heads, so RV is the number of heads that show up in the experiment, okay, and we have to find a probability distribution, okay? Like we said, the probability distribution is the list of the outcomes with their corresponding what? Probabilities. Now, all we need to do is to first find our outcomes, which will be what? Head, 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 tail, okay, for 3 coins, okay? Good. So this will be our sample space. Then next, you have to count the number of heads per the rule, okay? So this is 3, this is 2, this is 2, this is 2, this is 1, 1, 1, and then we have 0. So the possible values of the random process is that, and then they are defined over this domain or this set, okay? Very good. And then now, how do we get the probabilities? We said the probability of an event E, okay, is equals to the number of outcomes in the event, okay, over the number of outcomes in the sample space. Good. Yeah. So if that is the case, then the probability of this outcome, X equals to 0, will be how many, how many outcomes of this event type do we have in the sample space? It's 1. There's only 1 tail in the whole of the sample space. Out of 8 outcomes, we have 1, 2, 3, 4, 5, 6, 7, 8. We have only 1 unique tail. So that gives us what? 1 over 8, okay? So the probability will be 1 over 8. Very good. On the other hand, when it comes to 1, there are 3 different, okay, outcomes which have only 1 head out of a total of 8, okay? So that will give us 3 over 8 for the probability of the outcome 1. And then the probability for the outcome 2, we have 3 outcomes, okay, in the whole sample space. So that gives us 3 over 8. And then finally for X equals to 3, there is only 1 unique h in the whole sample space. So that gives us 1/8. Okay. So that is the probability distribution, okay, for the random variable, okay, defined as observing a head in the toss of what? 3 coins, right? But we can also write this distribution in a function form, okay, like we have below. Okay, how do we do that? We see the probabilities at the point 1 and 2 are the same, and the probabilities at the point 0 and 3 are also the same. So then we can combine them. We can say that the probability is 1/8, just like a piecewise function, okay? So the probability is 1/8 if x is what? 0 and 3. And then the probability is what? 3/8 if x is what? 1 and 2, okay? So we can rewrite this function, the probability distribution, as a function, okay, that's a PMF, okay, as 1/8 if x is equal to 0 and 3, and then what? 3/8 if x is equal to 1 and 2. Okay, so I'll give you some time to study this and ask some questions. So if you have any questions, you can ask at this point. Yeah, any question? Ojo?
No question at this point, sir.
Okay. Yeah, class, any question? Okay.
No, sir, for the moment, sir.
Okay, fine. So if that is very clear, then we continue from here. Okay. So based on what we've just looked at, then it means that we can also write the probability function, okay? Let me go back a bit. You see, we've written P of x is equals to that, okay? We can equally write it as because it's now a function it's now in a function form, we can equally write it as what? F of x is equals to this, okay? Meaning it's a function of x. But don't forget, even though it's a function, we are talking about a probability what? Function, okay? This is a probability function. This is not a deterministic function, but a probability what? Function. Okay. Okay. So with that understanding, then it means that you could be asked, okay, to find some unknown value, okay, or an unknown variable, given this time, given the probability distribution. So I have written the distribution in this form. F of x is equals to what? Kx, where x is 1 and 2, and then is equal to 3k times 4 minus x, where x is what? 3 and 4. Okay. So, and then 0 otherwise. 0 otherwise means on every other value of x, the probability is what? 0. Okay, and we are asked to evaluate the value for what? K. Okay. How do we do that? We know that the function was derived from the table. We use the table to derive the function, right? So if you've been given the function, the first thing to do is to go back to the table form. And in writing the value of the table, like we know, the probability distribution table, we always have x and p of x, okay? So we have to write out the values of x, which will be 1, 2, 3, and what? And 4. Then now, what is the probability? The probability is what is written here. That's the values of the probability. So when x is 1, okay, the probability is what? Kx is defined piecewise, okay? So when x is 1, the probability is kx, okay? But x, we are saying x is 1. So if the probability is kx, that will be k times 1. Okay, and k times 1 is equals to what? Is equals to k. Okay, the same way if x is 2, our function is defined as what? Kx. So x will be 2. So k times 2 will be what? 2k. Then if x is 3, this time we are on a different domain. So this becomes what? 3k into bracket 4 minus what? X. But x is 3. So it will be like this, 3k, okay, into bracket 4 minus what? Minus 3. Okay, which is equal to what? This will be 1, okay, times 3k. So we still end up with what? 3k. Okay. Then finally, if x is 4, we get 3k into bracket what? Into bracket 4 minus what? 4. Okay. And we know that 4 minus 4 is what? Is 0. So 3k times 0 will be what? 0. So the probability here will be what? 0. Okay. So with that understanding, then the next thing you do is we know that the sum of all probabilities is always equals to what? It's always equals to 1. Okay, the sum of all probabilities is equal to 1. So if that is the case, then we can easily write, if that is the case, then we can say that k plus 2k plus 3k plus 0 should be equal to what? Should be equal to 1. So the sum of all the probabilities here should be equal to 1. So we write this, okay? And then when we sum k plus 2k, that's 3k plus 3k, will give us 6k equals to 1. And to get your k, you just make k the subject, which will be 1 over 1.